Today we're going to be talking about the total response of of parallel RLC circuits. So this is similar to what we did back in circuits 1 with first order circuits. So RL circuits and RC circuits. But now we're going to have two energy storage elements. And we are going to start by looking at our most simplistic and or well-behaved cases, which would be parallel RLC circuits today, and then series RLC circuits next Wednesday after our test. After we learn the rules for the simple case, then we're going to try to adapt those rules to more general cases where we just have two energy storage elements, but they're not necessarily all in, everything isn't connected in parallel or series, okay? So let's look at the following circuit, okay? So I'm going to give myself a current source here, and I'm going to call this guy IS, like so. And this is going to be kind of like a single pole double throw switch. So I'm going to have a path over here that'll be terminal A, a path over here that'll be terminal B, and we're going to start with our switch closed at B, and it'll switch over to close at A at t is equal to 0. Our A path is just going to look like a short circuit. And then our B path is going to be a network which contains a resistor R in parallel with some inductance L in parallel with some capacitance C, like so. So I'm going to define a few quantities here that we are going to be interested in. The first of which is going to be a voltage V of t. So I'm going to draw that voltage here, plus on top, minus on bottom. This is V of t. So this is the voltage drop across the resistor, across the inductor, and the voltage drop across the capacitor, because all of those three elements are connected in parallel. Because it happens to be the voltage drop across the capacitor, we're going to have to remember the rules about how the voltage drop across the capacitor changes, in as much as it cannot change between t is equal to 0 minus and t is equal to 0 plus. If it did, we would be creating or destroying charge, actually would be transferring an infinite amount of energy, which can't happen, right? So this voltage is going to be constant from 0 minus to 0 plus. I'm also going to define a few currents here. So this is going to be my resistor current, IR of t. This will be my inductor current. Actually, let me sneak it down here on the bottom so that I don't run into anything. IL of t. And this will be my capacitor current, IC of t. So when we had our first order circuits, so our series RL circuit, or excuse me, our RL circuits and our RC circuits, what we saw was that our energy storage element usually started off with some amount of energy, and the equation that we got was effectively modeling how that energy storage element passed its energy on to the resistor to be converted into heat over time, okay? We have a little bit of a different thing here because we have multiple energy storage elements. So they're going to tend to interact with each other, as well as eventually passing that energy on to the resistor for it to be converted into heat as time progresses, okay? So the math is going to be a little bit more difficult than what we had for our first order system because of that interaction between the two energy storage elements, okay? So if I were to apply KCL during the transient condition, bless you, where that would be t greater than 0 plus, so anytime after our switch change states, what we would find is that our resistor current IR, our inductor current IL, and our capacitor current IC have to all add together to make 0, right? Kirchhoff's current law, we're at the point where our source has been disconnected. So on the right-hand side, we're only going to have the right-hand top node, we're only going to have those 3 currents exiting the node, add them all together, set them equal to 0. Well, hopefully we know that we can express all 3 of those currents in terms of that common voltage V that is present across all 3 elements. So for our resistor, that's just going to be Ohm's law, right? So we would have a factor of 1 over R times V. For our inductor, we are going to have an integral, right? So the voltage drop across the inductor is 1 over L times the integral from T naught to T of V of T prime dt prime, where those T primes are just dummy variables for time because I have T in my limits of integration. I'm going to have my initial condition to take care of. So that's going to be IL at time T naught. And now I'll have my capacitor current, which is just C times the derivative of my voltage with respect to time. And I'm going to set this equal to 0. So what we have here is an integro differential equation. Okay. So in circuits 1, we were dealing with a first order differential equation. Now we have a differential equation that also has an integral in it. And in some cases, that can make things very difficult. So what I'm going to do to make this less of a pain in the ass to handle is I'm going to just take the derivative of both sides of my equation. So I'm going to convert my integro differential equation into a second order differential equation because that's going to be easier for us to solve. Okay. I'm also going to rearrange the order of things. So I want to put my highest order derivative term first, and then I'm going to put my lowest order derivative term last. Okay. So if I take the derivative of the left-hand side, so let me just put taking the derivative of both sides yields. So I'll have C times the second derivative of my voltage with respect to time plus 1 over R times the first derivative of my voltage with respect to time. What happens when I take the derivative of an integral? They cancel each other out. So I'll have 1 over L times what I like to call my 0th derivative, which is just the original function, V of t. And what's going to happen when I take the derivative of that initial condition on the inductor current? It'll be 0 because that's a constant, right? So I have now a second order differential equation. And for reasons that I will not explain to you until literally a week from now, I'm going to divide through by a factor of C so that the coefficient on my highest order derivative term is going to be 1. Okay. So that's just going to look like the second derivative of my voltage with respect to time squared plus 1 over RC times my first derivative with respect to time plus 1 over LC times my voltage by itself. So this thing has to be equal to 0 somehow, okay? So in circuits 1, we guessed that our voltage in an RC circuit needed to be an exponentially decaying voltage. So I'm just going to make that guess again because it worked before, so why the hell not? Let's see what happens, right? So let's say that V of t is equal to A e to the st. Exactly the same guess that we used back in circuits 1. So if I plug this value in, so what's the second derivative of A e to the st going to be? So my first derivative is going to be S times A e to the st. Let's look here just really quickly, right? I'm having a bit of a brain fart, so I'll just do it formally just to cover my ass. So that's S A e to the st. My second derivative then is just the derivative of my first derivative, right? So that's I have a product of two functions here, right? So remind me how the product thing works. It's been a hot minute since I took math 241. So the first function, which is s times the derivative of the second, so that's going to be s squared ae to the st plus the second function times the derivative of the first.
Either or, as long as you split it up, multiply it back together, add it, split it back together, multiply it together. So it would be derivative of s times ae of st plus s times the derivative of ae to the st. So it would literally just be plus ae to the st. So we're taking with respect to.
Oh, I'm dumb. I'm so dumb. We're taking it with the derivative with respect to t, not with respect to s. So it's just this. Okay, sorry. I was like, that's not working out right. It's because I was actually already done and my brain just does not work today. Sorry for the lack of sleep. Yeah. Taking the derivative with respect to t, I'm just going to pull down that extra s. Great. Now this is going to work right and I'm going to look like less of a jackass. Wonderful. Okay. So I'm now just going to plug these second derivatives in, okay? So I'm going to have s squared ae to the st here. Then I'm going to have s over rc times ae to the st. Then I'm going to have plus 1 over lc times ae to the st is equal to 0. And I'm going to just pull my common factor of a out, put it on one side, pull my common factor of e to the st out, put it on the other side, and then leave what's going to look like a second order polynomial in the middle, right? So this would come out to be a times s squared plus s over rc plus 1 over lc e to the st is equal to 0. So much like we saw back in circuits 1, if A is equal to 0, this is technically a solution, but that is the solution for there was no energy stored in the system to begin with, and everything is 0. So we're just going to throw that one away because it's not really giving us any good information. E to the st will trend towards 0 if s happens to be a negative quantity and we wait long enough. Really, what I'm trying to figure out is what makes this guy in the middle here equal to 0, and that will give me my eigenvalues or my natural frequencies for this system. just like we did with our first order system, right? So I'm going to set this middle term equal to 0. So luckily for us, this is just a second order polynomial, or more commonly known as a quadratic function, right? So I can literally use the quadratic equation to figure out what the roots of this thing are. And so I'm going to do that right now. So I'm going to have two different s values. So I'm going to say s1 comma 2 will be equal to, and if my 8th grade math memory is with me today, I feel like the quadratic equation is negative b, where b is the coefficient on the s term here. So that's going to be negative 1 over RC plus or minus the square root of b squared. So I'm going to have 1 over RC comma squared minus 4 times a, which in this case, that's the coefficient on s squared, so it's just 1, times c, which is the constant term, which is 1 over LC. And all of this is going to be divided by 2a, so that's just going to put a factor of 2 on the bottom. What I'm going to do now is I'm going to incorporate that 2 that's in the denominator up into the numerator so that I don't have too many fractions all over the damn place, right? So that's going to wind up looking like negative 1 over twice RC plus or minus the square root of 1 over twice RC, quantity squared, minus 1 over LC. Are we all okay with that? Okay. So I have my two natural frequencies for my system. So now I want to introduce a couple of quick things here, okay? So we are going to say that there's going to be some term alpha, okay? And alpha is what's called the Neper frequency. And it's kind of sort of playing the role of what our time constant was, or the inverse of our time constant was, to put it in a better way, back with our RL and RC circuits. So this Neper frequency is describing how our signal is attenuating or decaying over time, okay? The Neper frequency is measured in Nepers per second, where a Neper is a dimensionless quantity. So we could literally just say that alpha is measured in per seconds and be perfectly okay with this thing, okay? So mathematically, our Neper frequency, specifically for a parallel RLC circuit, is going to be defined as 1 over twice RC. The other thing that we're going to define is our resonant frequency, omega naught. So resonant frequency is going to be measured in radians per second. And it wears a lot of different hats in electrical engineering, mechanical engineering, all of that kind of good stuff, okay? So in electrical engineering, what the resonant frequency represents, or the most common definition of it, is this is the specific frequency that the impedance of this network is going to look purely real. So at whatever this resonant frequency is, if we had that parallel RLC network, at that frequency, the only thing that we would actually see would be the resistance, because the reactance of the inductor and the negative reactance of the capacitor would wind up canceling each other out, okay? This is also the particular frequency where effectively our energy storage devices are doing their best job, meaning if I put a small input signal in specifically at the resonant frequency, I'm going to get the largest output signal out. So I get the most change in my system if I excite it at my resonant frequency, okay? So mathematically, our resonant frequency is just going to be 1 over the square root of LC in this case. So what that allows me to do is to express those natural frequencies of S1 and S2 in terms of my Neper frequency and my resonant frequency. So we could say that S1 comma 2 is going to be equal to negative alpha plus or minus the square root of alpha squared minus omega naught squared. Okay. So this is our kind of fundamental definition for how we are going to solve for S1 and S2 for any given circuit. Okay. So depending on the values of the elements in my circuit, I'm going to have 3 different cases, okay? So let's look at our first case, which is what's called an overdamped system, okay? So in an overdamped system, we will see that S1 and S2 are both real and negative, okay? So S1 would simply be negative alpha plus the square root of alpha squared minus omega naught squared. And S2 would be negative alpha minus the square root of alpha squared minus omega naught squared. Okay. In order for this to happen, so in order for S1 and S2 to both be real and negative, what has to happen is that alpha needs to be greater than omega naught. So I'm going to draw a graph here in a moment, but I'm going to essentially try to describe what's happening with an overdamped system, okay? So what we're going to see is some sort of exponential decay that's going to take a relatively long time in order to settle down to its final value. So instead of dropping to its final value quickly, it's just going to take a hot minute to get there because we have too much damping in the system that's not allowing it to change quickly enough, okay? So in this particular case, for an overdamped system, our general form for our response, and this is literally on the table that I gave you, which is part of the reason why I gave you the table, we are going to have, in general, y of t will be equal to a1 e to the s1t plus a2 e to the s2t, and I'm just going to put plus y at infinity here to account for a total response problem as opposed to a natural response problem. So if we have a forcing function that's going to make our voltage or current be some fixed DC value at t is equal to infinity, I've already got that part taken care of. Okay. Our next type of system that we're going to talk about is a critically damped system. So in a critically damped system, S1 is exactly equal to S2. Okay. And the implication of this is then alpha has to be equal to omega naught, right? So if I look at my expression for S1 and S2 above, if alpha is exactly equal to omega naught, everything under the square root sign dies, and I have S1 is equal to negative alpha and S2 is equal to negative alpha, okay? So if we try to use this relationship over here that I have as y of t for our response, we'd actually run into a little bit of a problem because we have two energy storage elements, and so we should have essentially two different initial conditions on our system, right? So however much energy we have stored in our capacitor and then however much energy we have stored in our inductor will cause our system to behave in different ways. Well, if I literally just plug in S1 is negative alpha and S2 is negative alpha, I could just add those two guys together. That breaks things because it looks like I have a first order system. So instead, we have to adapt our response equation. And so we're going to have something like y of t is equal to a1 times t e to the negative alpha t plus a2 e to the negative alpha t plus y at infinity yet again. So we have to have that extra t term there on our first parts of that expression in order to force our system to include the effects of both initial conditions, okay? You'll go into much more detail about where that guy comes from in Math 245 for what it's worth. Or you should anyway. Okay. So our third situation is what's called an underdamped system. Okay. So in an underdamped system, S1 is the complex conjugate of S2 and vice versa. So this criterion happens when alpha is less than omega naught, okay? So if we scroll up here to our boxed in representation for S1 and S2, if omega naught is greater than alpha, then what's under the square root sign will be a negative quantity. So I'll have negative alpha plus some imaginary number, and then negative alpha minus that same imaginary number. Well, that's complex numbers that are conjugates of each other because they have the exact same real part and imaginary part, but just the sign on the imaginary part has been switched. Okay. So in this case, if we plugged in essentially Euler's identity into this original y of t for an overdamped system relationship, what we'd wind up getting is y of t after several trig identities and algebraic steps. We'd wind up getting the relationship b1 cosine omega dt plus b2 sine omega dt, all multiplied by e to the negative alpha t plus y at infinity, okay, where omega d is simply the square root of omega naught squared minus alpha squared. Just for what it's worth, I'm going to point something out here that you guys all actually already know, but it's not intuitively obvious. B1 cosine omega dt plus B2 sine omega dt could be expressed as a single sinusoid, okay? I'm not going to do that in this class. I'm always going to express it as the sum of two sinusoids with no phase angles as opposed to a single sinusoid with a phase angle. Once we learn how to use the Laplace transform to analyze circuits in circuits 3, that's when we'll compact this stuff into a single sinusoidal function. But right now, because the process for analyzing these second order systems is going to involve me setting up a 2x2 system of equations, I need those guys split in order to figure out how to set up that system. Okay. So these are our 3 different types of systems that we could possibly see for any parallel RLC circuit, depending on what the component values are. It's always going to be either a critically damped system, an overdamped system, or an underdamped system. And so I just want to give you a quick graphical representation of kind of what the difference between those things are. Okay. So very loosely, we might see something like this. So this is T. I'm going to call this Y of T. And in purple, I'm going to do something characteristic of a critically damped system. So critical damping might look something like this. Looks like a simple exponential decay, okay? Fairly reasonable, especially if one of our natural frequencies is much larger than the in magnitude than the other natural frequency. It's going to look more and more like it's a single exponential function, okay? Now I'm going to do overdamped in blue. So in an overdamped system, we're going to have almost the exact same shape of the response. It's just going to take a lot longer to settle to its final value. So we might have something like this. And then for critical damping, sorry, underdamping, thank you. Should have brought notes instead of just freestyling it, but it's too late now. So what we're going to see in an underdamped system, we have some oscillation, right? We have cosine of omega d and sine of omega d. We're going to see an exponentially decaying sinusoidal signal. So it's going to get down to the final value, which in this case, I'm making it look like it would be a value of 0, but it's going to overshoot it and then ring. And it's going to continue to ring until those sinusoids damp out to essentially 0. So it would be something akin to this. And so on and so forth, where the envelope of this guy looks like an overdamped response, converging to some single point from both the top and the bottom, okay? So those are our 3 different basic things. And then just to be really clear here, because some of the homework problems that I'm going to assign you guys for an underdamped system, if it's very close to being a critically damped system, it's not going to ring as much. If it's really underdamped, it's going to ring a whole bunch. So when you do your simulations of things, if it's close to being a critically damped system, you might not see a ton of overshoot and all of that kind of stuff. It would look pretty darn close to a critically damped system. So don't think you did it wrong just because you don't see huge amounts of sinusoidal oscillation. Okay, so I've hit you guys with a ton of stuff. And so what I want us to do now is to work an example problem so that I can show you guys how I expect you to use the table I've provided you, okay? Because it is my goal with this table that I created to eliminate a large portion of the background calculus that would be going on in order to solve these systems. Because it's the same calculus every damn time. Let's not waste our time. Let's just use a table and plug shit in. Kyle, you had a question? Yes.
Is underdamping always sinusoidal?
So if we look at our mathematical expression, the short answer is yes. But once again, if we are very, very close to critically damped, then we're going to see that essentially omega D is going to be a small number. And so it takes a very long time for us to observe those oscillations. It might decay before we see like a lot of sinusoidal ripple. Okay. All right. So let's just work an example with the straight circuit that we had from the beginning of class, and then we're just going to throw some numbers at it. Okay. So let's call this a 4 amp source. So here's my resistor. So Kaylee, pick a number between 1 and 20. 12. Great. 12 ohm resistor. Quinn, pick a number between 1 and 20. 1 over 20 Henry inductor. Sam, give me a capacitor value in millifarads. 7 millifarads. Okay. So this is the circuit that we are going to attempt to analyze. And so what quantity might we be interested in? Josh, pick something. Current or voltage through any of those elements. So the voltage drop across the capacitor, so that's going to be the voltage drop across everything. So I'm just going to label that as V of t. Carl, pick another quantity, just one of the currents at random. Current through the resistor. Okay. So okay. So we're going to see in our process here, we're going to have to pay attention to at least one other quantity. Okay. So generally speaking, I usually pay attention to the voltage drop across the inductor, which is the same as the voltage drop across the capacitor here, the inductor current, and the capacitor current. So I usually need to know everything that's going on with my energy storage elements in order to wind up setting up my system of equations. So even though we're not explicitly trying to solve for this, I'm just going to make a note here. Hey, we're going to pay attention to IL of t, and we're going to pay attention to IC of t. So I'm trying to think of what I want to do first. And really, I'm trying to remember of how I set up the homework assignments for this stuff like 5 years ago. So I might have the order slightly different than how I have you guys do it in the homework, but it's going to be roughly the same process. So let's start by analyzing this circuit at t is equal to 0 minus. Okay. And we are only going to bother with solving for what's going on with our energy storage elements at t is equal to 0 minus. We are literally not going to pay any attention to that resistor current until the very end of the problem. And I'll explain why we have to take that approach as we go through this procedure, okay? So at t is equal to 0, our A terminal is just open circuited. We have our 4 amp source. Here's our 12 ohm resistor. What is our inductor going to look like at 0 minus? Short circuit. What's our capacitor going to look like at 0 minus? An open circuit. Great job. So I'm going to call this voltage right here V of 0 minus. This is going to be my inductor current, excuse me, my capacitor current at 0 minus. And here's my inductor current at 0 minus. As I mentioned earlier, we're literally going to ignore voltage and current across the resistor. We're not going to bother solving for them at all because it is utterly pointless until we're at the very end. Okay. So who can tell me what any of these three quantities might be?
Well, 0 minus 4 amp, and then negative 0 minus is 0 amp.
So IL of 0 minus is 4 amps. I agree with that. All of our source current will flow through the short circuit representing the inductor. I agree with that 100%. IC of 0 minus is going to be 0 amps because we know that no current flows through an open circuit. On board with that wholeheartedly. Somebody else tell me what's going on with V at 0 minus. What was that? 0. You're correct. Can you explain why? No. So the capacitor is in parallel with the inductor. The inductor looks like a short circuit. The voltage drop across a short circuit is always 0. So we should always see that IC is going to be equal to 0 amps and V is going to be equal to 0 volts at T is equal to 0 minus for any parallel RLC network. It literally can't be any other way, right? Because our capacitor is always going to look like an open circuit. So the current flowing through it's always going to look like 0 amps. And our inductor is always going to look like a short circuit, which means the voltage drop across it is always going to be 0 volts. So those two bottom initial conditions there are the same for every circuit, essentially. All right, so how do we feel about our analysis at T is equal to 0 minus? Anybody have any questions, comments, or concerns? All right. Now we're going to analyze the system at T is equal to 0 plus. Okay. So at T is equal to 0 plus, my current source is going to be connected to terminal A, and B is going to be open circuited. Here's my 12 ohm resistor. What is my inductor going to look like? So a 0 amp current source. What's a 0 amp current source? An open circuit because no current flows through an open. So I'm going to represent my inductor here. Sorry, let me scooch this guy over so that it's looks the same or it's going to bother me. So my inductor is going to look like an open circuit. What's my capacitor going to look like? I disagree. It will look like a short circuit because a short circuit forces the voltage drop across it to be 0, right? So the voltage drop across the capacitor stays constant. Since the voltage at 0 minus was 0 volts, it has to continue being 0 volts at t is equal to 0 plus. So we'll have a short there. So this will be V at 0 plus. Here's IC at 0 plus. Hold on, I have made IL at 0 minus was 4, not 0. So we should have a 4 amp source for our inductor current, right? Sorry about that. So four amp source down like so. Here's V at 0 plus. Here's IL at 0 plus. So let me double check this just because we made a mistake a moment ago, right? So we know that IL at 0 plus must be equal to IL at 0 minus, which was 4 amps. That's where that 4 amp source came from. The direction is down because IL was defined to be down. Okay. We also know that V at 0 plus must be equal to V at 0 minus, which is 0 volts, because the voltage drop across a capacitor cannot change abruptly. And that's where that short circuit replacing my capacitor came from. Okay. So the only thing that we really need to find then is IC at 0 plus. Anyone have any thoughts here? -4. Absolutely right. So for those of you that didn't intuitively see that it's -4, the current that's being pushed by our inductor, or that 4 amp source, it has an option of flowing to the left and trying to flow through a 12 ohm resistor as it goes up, or going to the right and flowing through a short circuit. It's definitely going to go to the right and flow through the short. Since the inductor current is flowing up and the capacitor current is defined as flowing down, that's where we get the -4 from. So great job. Okay. For this particular circuit, since there is no source connected during the transient condition, everything is going to be 0 at infinity. Right? If we need to draw it out just for the hell of it, I can do it. So at t is equal to infinity, our current source would be closed at terminal A. So here's our 4 amp source. B is open circuited. Here's my 12 ohm resistor. At t is equal to infinity, my inductor is going to look like a short. And at t is equal to infinity, my capacitor is going to look like an open. So here's V at infinity. Here's IL at infinity. And here's IC at infinity. We can see by inspection, IC at infinity is 0 amps. V at infinity is 0 volts. And I believe we can all agree that IL at infinity will also be 0 because there's no source connected to push any current through that short circuit. All right. So we've done all of our circuit analysis for this problem. Now we have to go do the math effectively, okay? So what we're going to do first from the math side of things is we are going to determine whether this circuit is overdamped, critically damped, or underdamped so that we know which equations to use, okay? So we're going to check that by calculating alpha, which is 1 over twice RC. So that would be 1 over 2 times 24 times 7 times 10 to the minus 3. Let me find a calculator because I can't do that reliably in my head. No, that 24 should be a 12. I did the 2 times 12 in my head and screwed that up. Sorry. Making all kinds of mistakes today. 2 times 12 times 7 times 10 to the minus 3. I got 125 over 21 neppers per second, or 5.9523 and some change, so I'll just leave it there. Neppers per second. Because I have made at least 2 mistakes today, can somebody verify that I put that in my calculator correctly? Okay, Seneca is shaking his head yes, so I'm going to say he and I are right. The next thing that we're going to calculate is omega naught. Omega naught is the square root of 1 over LC. So that's going to look like the square root of 1 over 20 times 7 times 10 to the minus 3. And I get 53.452 and some change radians per second. For what it's worth, I'm now going to store that guy in my calculator as B, and I'm going to store this guy in my calculator as A for a little bit later. Okay. So based on these results, is this system overdamped, critically damped, or underdamped? Underdamped, okay? So because omega naught is greater than alpha, this is an underdamped system. So that means that we are going to use the underdamped part of our table, okay? So just for the hell of it, while I'm doing it, I'm going to just calculate omega d, where omega d is the square root of omega naught squared minus alpha squared. So square root of what I have in my calculator as b squared minus what I have in my calculator as a squared. And I wind up getting 53.1197. So let's call that 53.120 radians per second. And I'm going to store that in my calculator as C for when I need it later. Okay. I'm going to open up the table here, which I believe I just have on my PDF viewer. Okay. So we have a parallel RLC circuit. And so its constituent equations are going to be alpha is equal to 1 over 2 RC, which we already used. Omega naught is the square root of 1 over LC, which is a slightly different representation of that exact same thing, so it doesn't really change anything. We have this relationship here, y of t is equal to b1 cosine omega dt plus b2 sine omega dt times e to the negative alpha t plus y at infinity, blah, blah, blah. I also gave you guys this derivative thing here, okay? So essentially what we're going to wind up doing is we are going to make a choice, and it's dependent on what we're ultimately trying to solve for, as what we are going to consider y of t to be. So this is a binary decision, okay? It will always be either a capacitor voltage or an inductor current. And then we are going to use the derivative-based relationship with that thing. So if I have a capacitor voltage, then my derivative-based relationship is my capacitor current. If I use my inductor current as y of t, then my derivative-based relationship is the inductor voltage, okay? So that's where our system of equations is going to come from. So y is always capacitor voltage or inductor current. dy by dt is the derivative-based relationship based on what y is. So I hope this will make more sense in a moment, but if we go back to the top, our ultimate goal in this problem was to solve for our capacitor voltage and then also that resistor current, okay? Now, this is the first time we're actually bringing things back around to what's going on with the resistor, okay? So I'm going to ask you a question that I believe is an easy question. Does a resistor have a derivative-based relationship for it at all? No. So we are never going to solve our system directly for what's going on with a resistor. What I'm going to do instead is I'm going to solve for that capacitor voltage because I know that that voltage is in parallel, or the capacitor is in parallel with the 12 ohm resistor. Once I know what that capacitor voltage is, I can just divide it by 12 ohms to find that resistor current, okay? So the only thing that I'm ever going to directly solve for is capacitor voltage, capacitor current, inductor voltage, or inductor current. Anything having to do with a resistor has to come in after we know at least one of those other quantities. There is no other way to do this, okay? I realize we're running short on time, so we might wind up finishing up this example later, but we can make some progress, okay? So since I can kill two birds with one stone just by knowing what my capacitor voltage is, I'm going to treat that as my y of t quantity, okay? So coming way back down here, I'm going to say that Vc of t, or V of t, because we've been calling it V of t the whole time, is equal to B1 cosine omega dt plus B2 sine omega dt e to the negative alpha t. And because we found that our capacitor voltage was 0 at infinity, I'm just going to leave it here. So what happens if I evaluate this at t is equal to 0? So what happens to a cosine function if t is equal to 0? It's 1. What happens to my sine function if t is equal to 0? It's 0. What happens to my exponential function if t is equal to 0? It goes to 1. So essentially, the only thing that's going to survive is B1. So I already know what one of my two coefficients is. So numerically, B1 is 0 volts. So not even going to really have to use my calculator to solve this system. It's going to be pretty damn simple. Now I need to go into my derivative-based relationship, right? So I know that the current flowing through a capacitor is equal to C times the derivative of the voltage with respect to time. So this is going to be C times, and now I'm just going to go to my table because I already did the derivative for you. Can't remember what this is off the top of my head. If there's an extra table, that would be great. Thank you. So now I'm just going to the dy by dt bit, and I'm just going to write this stuff down, right? So that's going to look like omega D B2 minus alpha B1 cosine omega dt minus omega D B1 plus alpha B2 times the sine of omega dt. Close that guy, e to the minus alpha t. Okay. Well, what happens if I evaluate this guy at 0 plus? Once again, my cosine function is going to look like 1. My sine function is going to look like 0. My exponential function is going to look like 1. And so essentially, all that's going to survive is c times omega d b2 minus alpha b1. Well, alpha times b1 is 0 because b1 is 0. So from this, I could say that my coefficient b2 that I'm ultimately trying to solve for is just going to be IC at 0 plus divided by C times omega D. Did I algebra that correctly? I'm just moving C times omega D over to the left-hand side. IC at 0 plus was negative 4 amps. C was 7 times 10 to the minus 3 farads. Omega D from up here, which I stored in my calculator as C, was 53.120 radians per second. Kind of running out of room, so I'll put it down here. I'm literally just plugging that stuff into my calculator. So I would have negative 4 over 7 times 10 to the minus 3 multiplied by what I have stored in my calculator as C. And I get negative 10.757 and some change volts. And now what I can do is literally just plug in my values for B1 and B2 into my response equation. So I can say that VC, or V of t, during the transient condition is going to be negative 10.757 sine 53.120 t multiplied by e to the negative, let me scroll up here and find alpha, 5.952 t volts. To make that look prettier. My resistor current that I'm interested in, IR of t, is just V of t over 12 ohms. So take that answer, divide it by 12, and I get negative 0.896 and some change sine 53.120 t e to the negative 5.952 t amps. We don't have enough time to do it today, so what I'll kick things off with on Wednesday, and I probably will need a reminder, is to show you guys how we can verify this using LT Spice.